Welcome to the massive open online course on Aspen Plus. In today's lecture, we are going to discuss about the electrostatic precipitator. Electrostatic precipitators, they remove the solid particles which are suspended on a gas stream using electrostatic forces. Most particles in a gas stream, they carry some amount of electric charge, but that is not enough for collection. Therefore, if additional charge is given to those particles, then it is easy for collection. And it has been schematically shown in this help file of Aspen Plus. Here you will find a high voltage power supply, and this one is at the lower voltage. This one is an electrode, and this one is another electrode plate or a dust collector plate. This electrode dissipates some electron at a higher voltage. And this electron gets attached with the gas molecule. And those gas molecules are ionized. And after getting ionized, these gas molecules get attached to the dust particles which are suspended in the gas stream. And this dust particle will be attracted by this collection electrode, and they will release their charge over there. And dust particle will fall down, and there will be a dust collector over there through which the dust can be removed. So that is the basic principle of an electrostatic precipitator. Usually there are two types of configurations that are available for electrostatic precipitator. One is plate type configuration. Another is the tube and wire type configuration. In plate type configuration, there will be an electrode and there will be a collection plate. But in tube and wire configuration, it will be a tube which will be the collection plate, and there will be an electrode which will dissipate the electrons for ionizing the gas molecule. And these tubes can either be with a square arrangement or hexagonal arrangement based on the requirement of the end user. So the arrangement is something like this. The dirty gas enters at one end and the clean gas gets released from the other end. In between, there will be these parallel plates, or there will be this tube and wire type of arrangement, which are actually the electrostatic precipitator configurations, and dust will be collected at this end. That's how these electrostatic precipitators are designed and used. Like any other solid separators, electrostatic precipitators also can be run in two modes. One is simulation mode and another is design mode. In other words, simulation mode, also called rating, and design mode operation is called sizing. In simulation mode, you have to mention the number of plates, the plate height, plate width, that is the plate precipitator configuration, and the number of segments. And there are some separation efficiency methods for which the number of segments have to be specified. We will learn them later. And for the wire and tube arrangement, you have to specify the tube radius, tube length, number of tubes, spray electrode radius. In short, you have to specify the tubular precipitator configurations. And once you specify them, you can find out the separation efficiency, power required, pressure drop, precipitator width, etc. And in the design mode, you have to specify the separation efficiency that you want to achieve. And you have to specify the gas velocity and maximum dimensions of the precipitators, which eventually will design the number of plates and tubes of the precipitator and the power required and pressure drop that will be required for that operation. So these are simulation mode and design mode of operation of electrostatic precipitator. Now, ESP model that is available with Aspen Plus, they usually model with high dust concentration, that is over 10 to the power 11 particles per meter cube or 0.1 kg per meter cube. Otherwise, the results will not be reliable. And usually, the gas velocity should be between 1 and 2.5 meter per second. And if it is more than 3 meter per second or less than 0.5 meter per second, then the Crawford model, which is one of the efficiency models that we will learn later. So this Crawford model will not be accurate for pressure drop calculation and efficiency. But if you want to use the Swarovski model or Deutsch model, then the gas velocity may be from 0.15 to 5 meter per second. So you have to see what is the gas velocity of your system. Based on that, you have to choose the separation efficiency model. Now, these are the separation efficiency models which can be used for an electrostatic precipitator. There are mainly three types of model. One is Crawford model, and then we have Deutsch model and Swarovski model. In order to understand these models, let us first open the Aspen Plus simulation window and look at the model parameters. Then we can tally between what we learn over here in the help file and what is available in the Aspen Plus simulation window. So this is the Aspen Plus simulation window, and you can get the solid separator over here. This is the gas solid separation using dry electrostatic precipitator. So you can just bring it over here, connect the feed line. This is the gas and this is solid. Okay. Now let us open the block specification, and you will find over here the models. So there are three types of model. One is regular solid separator model, which you know already. And there are two types of model, plate or tubular, which we have already discussed. Now, suppose you choose plate type, then again the mode of calculation, it will ask whether you want to run it in simulation mode or design mode. And then the calculation method, which we are now going to learn, it is three types of calculation method: Crawford, Deutsch and Swarovski. Now, overall, the separation efficiency is defined by the mass outlet flow rate of solid by the total mass flow rate of the inlet solid substream. That means whatever the amount of solid that has come into the system and whatever the solid that is coming out of the solid stream, so ratio of that is called the overall efficiency. That means how much solid we could recover in the dust collector. Crawford model in detail you will find over here, Air Pollution Control Theory by Crawford, Chapter 8, Electrostatic Precipitation. It's an old book, but you will get the information over here. Now the separation efficiency is given by this particular model equation, where CNVS is the particle concentration at XS, where XS is the point at which all particles have acquired a saturation charge, because the particles will also have a capacity of accepting the charge. So when it will take the charge up to its full capacity, that is the point. So point at which all particles have acquired a saturation charge. So that is the XS, and CNVS is the particle concentration at XS, and CNVO is the particle concentration at the inlet. So the inlet, so this is the dust plus gas, that is feed. So the concentration of dust over here, okay, so that is exactly is the NVO. And then L is equal to the plate length. QPS is particle saturation charge. EC is equal to collecting field strength. C is the Cunningham correction factor. Mu is viscosity of the gas. D is diameter of the particle. W is distance between wires and plates. And V is actual velocity through the precipitator. So this one we are talking about V, the actual velocity through the precipitator, which should be between 1 to 2.5 meter per second. Now in this model, these are the data you have to provide, like what is the particle diameter, what is the plate length, what is the distance between wires and plates. Suppose you choose the Crawford one, then you have to provide this information. You have to provide plate height, plate length. So here L, you have to provide the value. Number of plate has to be given. Then distance between plate and wire, that is W over here, that you have to provide. Some default values are already given in the system. You can use them or you can give the values as per your own requirement. Then viscosity of the gas will be obtained from the property database of Aspen Plus. W is the distance between wires and plate, so you have to specify over here. Then the actual gas velocity through the precipitator V. In the design problem, you have to give the minimum gas velocity and maximum gas velocity, and then the model will calculate the actual gas velocity based on the information that you give. But some of the things will be calculated by the model, such as the CNVS. This will be calculated by Aspen Plus. XS will be calculated. QPS will be calculated. EC will be calculated. Now, when you calculate XS, you need the distance between two wires, which will be provided by the user, and other specification like W, V, mu, D, already you know how to specify them. The electric permissivity constant is 8.85 into 10 to the power minus 12 C by Vm. Then the collecting field strength EC is defined by this equation, where you need to specify the VB, that is breakdown voltage, which you need to specify over here, breakdown voltage, and roughness factor of wire. By default, it is given 0.6. You need the information on atmospheric temperature, atmospheric pressure, and the operating temperature and pressure. All of them you have to give over here. And then CNVS, that is the particle concentration at the point where particles first have saturation charge. There you need the dielectric constant. The dielectric constant you have to specify over here of the mixed stream, or if you have a solid stream, obviously you have to have a solid stream. So whichever stream you have, the dielectric constant has to be mentioned over there. And the particle saturation charge, will be calculated by this equation, where everything Aspen would calculate from the previous expressions. So this is how the Crawford model works. Similarly, if you want to use the Deutsch model, then this is the equation you have. The separation efficiency is equal to 1 minus this expression to the power k, and the k value should be between 0.6 to 0.4. In the original Deutsch method, that is the paper written by Deutsch himself, k was said to be 1, but later it has been refined, and the later researchers have found the k to be between 0.4 to 0.6. Here you have an expression V mig d, and V mig d is migration velocity that can be calculated by this equation, where Qmax is the maximum loading of particle of size d, EP is the electric field of the precipitation area, and mu g is the dynamic viscosity of the gas phase, which will be available from the Aspen database. Qmax is calculated from this big equation where you have the lambda, that is free path length of the gas molecule, which will further be calculated from here, where Kb is the Boltzmann constant and dm is assumed to be 3.64 into 10 to the power minus 10. That is the diameter of the gas molecule. P is the pressure, T is the temperature of inlet stream. And another factor is there, UL. UL is the voltage applied to the loading area, and UP is the voltage applied to the precipitation area, and these two information will have to be given over here. So the moment you choose Deutsch, then these two things will be active. In Crawford model, they were not active, but in Deutsch model, they will be active. So these things for both parallel plate and variant tube type precipitators, they are given. And once you know the value of UL and UP, W is the width between the two plates. It is also an user input. So these are the user input, width, UL, UP. Okay. And RE and RT are the radius of spray electrode, radius of tube. Both of them you have to specify over here. Suppose you use the tubular type precipitator, then tube radius, tube length, number of tubes, and spray electrode radius. So this is RE. So this is RE. And RT is the radius of the tube. So this is tube radius. And the loading area voltage, precipitator area voltage, they are UL and UP respectively. Okay, so that's how you specify these values over here. Accordingly, EP, EL will be calculated, lambda will be calculated. You put those values over here, Qmax will be calculated. You put the value over here, V mig, or the migration velocity, will be calculated, and the area, AP, area is the precipitation area. So for parallel plate precipitator, AP will be 2 into H into L. H is the passage height, L is the effective length of the plate. So the effective length of the plate you have to provide over here. And then NP is the number of passage and NS is the number of sequential segment. So number of passage is one less than the specified number of plates. That means, suppose if you have, say, 3 plates, then there will be 2 passages. So if there are 3 plates, this is passage number 1, passage number 2. If there are 5 plates, then this is 1, 2, 3, 4. So it is always 1 less than the number of plates. Okay. So this is about the parallel plate precipitator. For wire in tube precipitator, the precipitation area is 2 into RT into pi into NT, where RT is the tube radius, NT is the number of tubes. So both you will specify over here the number of tube and the tube radius. Okay, so that's how you calculate AP. And V gas is the volumetric flow rate of gas. Swarovski model is almost same as the Deutsch model, but only difference is that the separation efficiency function suggested by Swarovski, it includes an exponent alpha, and that can be used as a fitting parameter between laminar flow condition and turbulent flow condition. So if the flow is laminar, then alpha will be 0, and if flow is turbulent, then it is alpha is equal to 1. So between the laminar and turbulent, you can give the values anything between 0 and 1. So that's how the separation efficiency will be calculated for Swarovski model. So it's almost same, only the structure is a bit different, but you need the same set of information to calculate the overall efficiency. These are about finding the separation efficiency. Then comes the pressure drop. The Crawford method calculates the pressure drop across the precipitator as this small equation where you need the information of gas density and gas velocity. Whereas for Swarovski and Deutsch method, the pressure drop can be specified directly, or you can use the polynomial function of the gas velocity, that is the second order polynomial. And you might remember when you learned the fabric filter, you came across a similar kind of function for pressure drop. Okay, the similar kind of function is applicable over here also. And then the required power. For power, you need two information. One is the overall efficiency and another is the volumetric gas flow rate. The power can be calculated. And V gas, that is the gas velocity, that can be calculated by using the information of the vapor mass flow rate that is obtained from inlet stream condition. Rho gas is also obtained from the inlet stream condition. H is the passage height, is the input parameter. W, NP, all of them are input parameters. And wire and tube also the similar kind of equation. Only thing is that because of its structure, the calculation of area will be a bit different. But the inputs that are required already know where you have to give those inputs, either plate type or tube type. You have to provide the geometrical information of them. Now, ESP model can be used for separation of fine particles of the range of 0.01 to 10 microns. And about the particle concentration, I have already told you before. And this is the design mode calculation. If you use a parallel plate precipitator, then V gas will be calculated based on this equation where alpha is equal to 0.791 and beta is equal to 3.098. And these constants are calculated by geometric considerations. So that's how the V gas is calculated. And based on the gas velocity, L, NP and H are calculated in this fashion, because in design mode you have to provide the information on the separation efficiency, right? So once you give the separation efficiency, it has to calculate the length of the plate, the width of the plate, number of plate that is required for the system. So all those dimensions will be calculated by Aspen Plus using these equations. Similarly, wire and tube precipitator also has its own set of equations. You can go through them and understand it better. Now let us solve an example problem so that we can understand the application of ESP better.